The Lockheed P-38 Lightning was the first American fighter to fly faster than 400 miles per hour in level flight. Test flights of the YP-38, the prototype vehicle for the production P-38, revealed problems initially thought to be tail flutter. During high-speed dives approaching the speed of sound, the aircraft would shake violently, and the nose would tuck under, negating elevator or rudder input. Flutter was ruled out as the P-38's tail was skinned with aluminum, making it structurally rigid. After extensive wind tunnel tests were completed, it was revealed the instability was due to compression. At transonic speeds, air compresses, forming shock waves that behave very differently than air moving at slower speeds. The P-38's center of pressure, where the forces of lift and drag are exerted, actually moved back toward the tail when flying transonic. The solution was to install dive flaps that actually changed the geometry of the wing, keeping it effective in a transonic dive.
There was a gentleman here at the labs named Ezra Kocher who had this great idea that we needed a research airplane to test the transonic regime as well as going supersonic. On the other end of the spectrum, the NACA, or the National Advisory Committee for Aeronautics, which was charged with exploring kind of the basic science behind flight, had a similar idea. So the two organizations got together and decided we're going to create a research airplane. They called it the X-1, and that was really the beginning of the research airplane program. So we were looking at contractors who could build an experimental plane, but all of the traditional ones were busy cranking out airplanes by the thousands for World War II. Well, Bell Aircraft out of New York wasn't quite as busy, but Larry Bell, who headed the company, agreed that he could do this experimental plane. So between them and the Air Force and the NACA, they designed the X-1.
Since the .50 caliber bullet was known to be stable at supersonic speeds, the body of the X-1 was designed to follow its basic shape. The combination of the stable body shape, thin wings, powerful engine, and an all-moving tail allowed Air Force test pilot Chuck Yeager to be the first person to fly faster than the speed of sound. Yeager's supersonic flight was the most famous. However, the X-1 family of rocket planes and the research techniques employed by the Air Force became the pattern for all subsequent X-craft programs. The flight data collected by the Air Force and NACA over the X-1's 238 flights proved invaluable to U.S. fighter designs throughout the rest of the century. The X-1E reached a top speed of Mach 2.24, but its straight wing and structural material limited it from achieving higher speeds. The X-2 delivered valuable research data on high-speed aerodynamics and thermal effects. The first X-2 was destroyed on a captive flight, checking the craft's liquid oxygen system. The plane was jettisoned and fell into Lake Ontario, never to be recovered. The last flight in the program saw the second X-2 become the first manned aircraft to fly faster than 3 times the speed of sound. Unfortunately, the aircraft became unstable when its pilot, Mel Apt, attempted a banking turn at speed. Apt ejected, but never exited the ejection capsule to use his personal parachute. He fell for several minutes and was killed. The X-2 program was stopped at just 20 flights. NACA never had the chance to even commence detailed flight research with the aircraft. The search for answers to high Mach flight questions had to be postponed for 2 years, until the arrival of the most advanced of all X-planes. In 1954, NACA realized the need to continue studying hypersonic and spaceflight. They established required characteristics of what became the X-15 and presented them to the Air Force and Navy in July of that year. Before year's end, NACA, the Air Force, and the Navy entered into a tri-service agreement to develop and fly 3 X-15 research planes.
And the idea was what was the Wright Air Development Center at the time, one of AFRL's predecessors, was going to manage the early part of the program, the procurement, the design phase. Then the NACA was going to manage the flight test program, and the Navy was kind of a junior partner in this.
After the WADC, headquartered at Wright-Patterson Air Force Base, selected North American Aviation as the contracting partner to build the X-15, Reaction Motors was selected to provide a man-rated, throttleable rocket engine to power the craft. This one project combined disciplines from the majority of the Air Force's research laboratories: propulsion, human factors, materials, control systems, airframes and airfoils, ejection seats, telemetry, simulation, and instrumentation technology used in the X-15 was extensively researched and tested within the Air Force laboratories. High-speed wind tunnels were developed to test aerodynamic heating at speeds above Mach 5. Large centrifuges were built to test pilot response to prolonged gravity loads. 1958 saw NACA supplanted by the newly formed National Aeronautics and Space Administration, and the following year saw the first X-15 delivered to the NASA High-Speed Flight Station at Edwards Air Force Base in California. Scott Crossfield, North American Aviation senior test pilot, made the first unpowered glide flight of the X-15 on June 8, 1959. Because the rocket engine consumed large amounts of fuel, the X-15 was air-launched from the wing of a B-52 at 45,000 feet. The rocket engine provided thrust for the first 80 to 120 seconds of flight. The remainder of the normal flight was without rocket engine power and ended in a 200-mile-per-hour glide, landing on Rogers Dry Lake, adjacent to Edwards Air Force Base. The X-15 used conventional aerodynamic controls for flight in the dense air of the usable atmosphere. For flight outside the Earth's atmosphere, the X-15 used a reaction control system.
Pitch and yaw controlled the attitude of the airplane, and the roll thrusters control the roll as you swept back and forth, because of course the aerodynamic surfaces had no effect whatsoever at those altitudes.
The X-15 was the first X-plane program to use a realistic flight simulator to plan and practice mission profiles.
The simulator let us not only plan flights, plan out flights, but practice flights, and to see where deviations were beginning to build up and take those deviations out and nullify them out as much as possible.
12 pilots flew the X-15 over its career, with 8 earning their astronaut wings by flying the aircraft into space. Neil Armstrong, one of the first to fly the X-15, would later become the first man to set foot on the moon. Joe Engle, a later addition to the X-15 pilot fraternity, logged over 225 hours in space on the space shuttles Columbia and Discovery. The X-15 flew 199 times over an 8-year period. Technology and techniques developed for the plane would influence the space shuttle and other spacecraft.
By the time you got to Mach 8, you had been to Mach 6 in the X-15, and the profiles were identical. The glides were identical. We used same airspeeds, same height to set up the overhead approach. But the confidence was already there. We had routinely brought back the X-15. That was the most familiar and part of the whole flight when it got time to fly Columbia.
Experiments flown on the X-15 included thermal protection and navigation equipment used on the Saturn launch vehicles during the Apollo program. The X-15 flew faster than any fixed-wing manned aircraft at 4,520 miles per hour, flying higher than any aircraft at 67 miles. It was the first aircraft to use reaction controls in space. its pilots used the first practical pressure suit in space. It demonstrated winged spacecraft landing profiles later used by the space shuttle. Although the X-15 now sits in a museum, it gave the knowledge needed for today's designers for future hypersonic aircraft.
And we're going forward with research on a new Orient Express that could, by the end of the next decade, take off from Dulles Airport, accelerate up to 25 times the speed of sound, attaining low Earth orbit, or flying to Tokyo within 2 hours.
It was called the National Aerospace Plane, and that was started by President Reagan and his administration, and it was an idea to have a single stage-to-orbit scramjet-powered vehicle.
Although the National Aerospace Plane never flew, the X-30 program generated voluminous research data. Out of the X-30 effort came 2 programs that continued the quest for air-breathing hypersonic flight. High-Tech was an AFRL program that developed a functional ground-testable scramjet engine.
Scramjet is a supersonic combustion ramjet, and it's used for flight generally above Mach 5. Well, if we could use a scramjet to fly through the atmosphere, you could have a propulsion system that would go fast, but take all the oxidizer it needs out of the atmosphere instead of storing it in the vehicle.
Firing around 80 different times in the NASA Langley 8-foot wind tunnel, the High-Tech test articles allowed AFRL to develop the rules and tools of scramjet engine flight. Hyper-X was a NASA program that sprang from the canceled X-30. This 12-foot-long X-plane, looking like a scaled-down X-30, was the first air vehicle to be propelled by a scramjet engine, while the X-43 was a very successful flight program. Its engine used hydrogen fuel, limiting the range of the plane, and resulted in an engine that could not be transitioned into an operational vehicle. In 2003, AFRL transitioned the High-Tech test data into a new vehicle test program called the Scramjet Engine Demonstrator, or SED.
So the then Chief Scientist of the Air Force, Dr. Mark Lewis, came to me and he said, you know, SED just doesn't cut it, and I've got an idea. How about we designate it, give it an X vehicle, because that's what it really is going to be. And I suggest X-51. And the idea behind the X-51 designation was that he thought it was a good juxtaposition of the X-15 nomenclature of the hypersonic rocket-powered vehicle that was very successful in the late 1950s and the 1960s. It was the first practical scramjet engine that actually proved to the aerospace community that you could ignite and combust in supersonic air conventional fuels and power an aerospace vehicle of relevant size to perform a mission.
While the X-51 is comparable in size to the X-43, it circulates conventional jet fuel through the walls of its engine to keep the motor cool. This made for an engine that ran cooler and, by design, longer. In fact, the first flight of the X-51 lasted longer than all previous air-breathing hypersonic-powered flights combined. As well as using common jet fuel, the materials sourced for the X-51 were all readily available and common in aircraft construction. Other challenges the X-51 design team faced were aerodynamic heating, engine control, and flight control systems. Over a period of 5 years, AFRL researchers and partners developed and refined the X-51 engine and airframe design, preparing it for a series of flight tests that would prove the viability of the vehicle. These flight tests culminated with the 4th and final flight, when the X-51 flew over 230 nautical miles in just over 6 minutes over the Point Mugu Naval Air Warfare Center Sea Range.
And it went off, and sure enough, it went from like Mach 0.8 to like Mach 5.0 in about 20 seconds. The whole mission's about 2.5 minutes, much like the Kentucky Derby, right? You're just waiting to see it, and then all of a sudden you start seeing it going down, and you're like, oh my gosh, it's starting to slow down. And then I heard the Boeing chief engineer kind of go very coolly, he goes, yeah, we're out of gas. We just ran it out of gas. And I went, oh, I guess it went well, right?
Beginning with the X-1 and carrying through the X-51, AFRL is working to ensure that hypersonic travel will no longer be an impracticality. and successfully transitioned the related technologies to revolutionary game-changing capability for the U.S. The future of hypersonic vehicle design owes much to the X-51's flights, which have forged the path toward practical hypersonic flight.